Welcome back to the lecture series of design of hydraulic structures. So, in the last class, we had discussed about Blick's theory. Blick's theory was used between 1910 to 1925, and many hydraulic structures were designed using Blick's theory. So later on, there were a lot of failures due to undermining in the structures which use Blick's theory for the design of hydraulic structures. So Koshla's theory is an improved version of the Blick's theory, which came after 1925. So according to Blick's theory, the water creeps along the bottom of the contour of the hydraulic structures, and the total creep length is taken as a horizontal length plus the vertical length. Whereas in case of Koshla's theory, so water moves along a set of stream lines. They are called flow lines. So let us study Koshla's theory in detail. So I'll share the content. So in this particular session, we will take up Koshla's theory, and in the next session, we'll take up problem on Koshla's theory. Okay. So here, in this theory, according the concept of flow nets, he has used the concept of flow nets. So water moves along a set of streamlines. I've already discussed what is a flow net when we discussed about earthen dam, and we calculated the seepage to an earthen dam using a flow net. Okay, so here this theory also is based on the concept that water moves along a set of streamlines or flow lines. The steady seepage in the vertical plane of a homogeneous soil can be expressed by Laplace equation. So this seepage can be expressed in terms of Laplace equation, that is dou squared phi by dou x square plus dou squared phi by dou z square, where x and z are the two directions, x and the x direction and z direction parallel to the plane. Whereas y is perpendicular to the plane, we are not taking the y direction here. So phi is the flow potential, which is kh, where k is the coefficient of permeability of soil as defined by Darcy's law, and h is the residual head at the point within the soil. This equation represent two sets of curves intersecting each other orthogonally. So in flow net, you have two set of curves. One is the streamlines or the flow lines. The other one is equipotential lines. They are called equipotential lines, are orthogonal to this flow lines, which you already have studied about this. The resultant flow diagram showing both the curves is called as a flow net. Okay, so you can see here, these are the streamlines. These are the streamlines, which is any water particle which flows from upstream to downstream side will follow a path. That particular path is called as a streamline. So you can see there are many such streamlines like this, which are which has its own path. So when this is the head at this point, that will be the depth of water in the reservoir, where here it is normally atmospheric pressure. The hydraulic head will become zero when it comes to the downstream side. Along CD it will be zero. So if you measure the potential of this stream flow at any one particular point, so it will be same at, yeah, even at other different streamlines. So every streamline possesses a head equal to h1 while entering the soil. So when it enters the soil, there will be some head. When it emerges to the downstream end into the atmosphere, its head is zero. That means here it will become zero. Here it will become zero. The head h1, why this there will be loss? The head h1, which was here, will become zero at the downstream side. This is because head h1 is entirely lost during the passage of water along the streamline. This happens because of friction. Because of friction, there will be energy loss during the movement of water, and finally this head at the point b, which was h, will be become zero towards the downstream side. Okay, so at every intermediate point in its path, so any point you take, there will be a certain residual head. Here the head will be h, here there will be a head, some value of head will be there, but it will be less than this, less than the head which was at b, which was at B. So similarly, as you move, as it moves forward, the head goes on decreasing, and at every point there will be a residual head. So this head will be dissipated because there is some length further to travel, and in the downstream it will become zero. This is applicable to every streamline, and hence there will be points on different streamlines having the same value of residual head. Say this streamline will have a residual h. Say if it is say some 10 meters or so, and same head will be present on this, and at some other point on the second streamline, on the other streamline the residual head will also be 10 meters. Again, you can find such points on the different stream lines where the residual head is same. So the line joining the points of equal residual heads on the streamline is called equipotential line. So these lines are called equipotential lines, and they are orthogonal to the streamlines. Okay. Uh, so every particle on the line AB has a residual. Here, every particle on this line will have a residual head H, and CD will have a residual head 0, and hence AB and CD are also equipotential lines. So AB is an equipotential line with head H, and CD is an equipotential line with head 0. In between you will have many other equipotential heads like this, which will be joining the stream lines or the flow lines at points where there are equal residual heads. Okay, so as the water seeps through, the seepage water exits a force at each point in the direction of flow and tangential to the streamline as shown in the figure below. So it will exert a pressure, and that will be tangential to this curve. So here it will be like this. Here you can see that the direction is changing, and as it is moving towards the downstream end, it is almost becoming a vertical, and at the exit it will be totally vertical. So the seepage water exerts a force at each point in the direction of flow and tangential to the streamlines as shown in the figure above. The force F has an upward component from the point where the streamlines turns upward, and for soil grains to remain stable, the upward component of this force should be counterbalanced by the submerged weight of the soil grain. So this force has to be this force F, which is tangential to this, it has to be counterbalanced by the weight of the saturated soil grain. So if this is acting like this in the upward direction, here the soil particle should be counterbalanced by the weight of the soil grain. At every point there will be weight of the soil grain which will be acting downwards, and this force will be tangential to the streamline. So this has to counterbalance this force. Okay, so the force has a maximum disturbing tendency at the exit because it will be totally vertical. The disturbing force at any point is proportional to the gradient of pressure of water at the point. So it will be proportional to the exit gradient. This gradient of pressure at the exit is called as a exit gradient, which is denoted by dp by dt. dp by dt. Okay, so uh, in order that the soil particles at the exit remain stable. So if it does not remain stable, what happens? The soil particles will be removed at the exit. But once a soil particle is removed at the exit, what happens? The undermining starts taking place and the backward erosion, which results in piping. So here that should not happen. That means the piping should not happen, or the undermining should not happen. Means the exit force F here should be balanced by the weight of the saturated soil particle at the exit. So that is what it says. In other words, the exit gradient should be safe. The exit gradient is said to be critical when the upward disturbing force on the grain is just equal to the submerged weight of the grain at the exit. So it is critical. So if it exceeds, if the force exceeds the downward submerged weight, then piping will take place. So an exit gradient equal to 1/4 to 1/5 of the critical exit gradient is ensured so as to keep the structure safe against piping. So the exit gradient, a factor of safety is used. So the factor of safety is 1/4 to 1/5 of the critical exit gradient is used. Okay. So this is what is the condition for this critical exit gradient? We will see. The submerged weight Ws of unit volume of soil is given by this expression, which you have studied in geotechnical engineering. The submerged weight is given by gamma W, that is density of water into 1 minus N into SS minus 1, where gamma W is the weight of water, SS is the specific gravity of the soil particle, N is the porosity of the soil material. For critical conditions to occur, this force F, which is at the exit point, should be equal to this Ws, submerged weight Ws. So F is the upward disturbing force on the grain. So the upward force F is the pressure gradient at the point, which is designated by dP by dL, where P is the pressure and L is the length of the water seepage. That is equal to gamma W into dH by dL. So dP is equal to gamma W into dH. The pressure is equal to density of water into the head at that particular point. So gamma W into dH by dL is the F. F. So Ws is this expression. Substituting F and Ws here in this equation, because the force should be equal to the submerged weight of the soil, the upward force. This is a disturbing force. That disturbing force is given by gamma W dH by dL, which is written on the left hand side, and on the right hand side expression for Ws is known. So that is written here, gamma W gets cancelled. So dH by dL, the pressure gradient or the hydraulic gradient is equal to 1 minus N. This is a critical exit gradient, which is equal to 1 minus N into SS minus 1. This is the condition. This one you have to remember. So coming to the Koshla's method of independent variables, for so using Koshla's method, we can determine the pressures and exit gradient for seepage below a weir or a barrage. I'll just go to the next slide. Yes. So here the explanation is given. So in order to know as to how the seepage below the foundation or a hydraulic structure takes place, it is necessary to plot the flow net. So, to study the seepage flow net has to be plotted. And see, these flow nets are represented, the two curves, set of curves, orthogonal curves. That is, one is the flow lines or the stream lines, and the second one is the equipotential lines, which are orthogonal to each other, can be represented by this Laplace equation. But these are complicated methods and time consuming. Solving this Laplace equation will take a lot of time. So therefore, for designing hydraulic structures, Koshla has evolved a simple and quick and an accurate approach called method of independent variables. So instead of studying the solving the Laplace equation, which represents the two curves of the flow net, he has evolved with a simple and quick, accurate approach called method of independent variables. Here, what is done is a complex profile like that of a weir is broken into a number of simple profiles. So, if there is a profile like this, if there's a profile, so here is the upstream side, and here there's a barrage or a weir, and then the downstream side. So there will be a sheet pile and the upstream face, and there will be an intermediate pile somewhere here, and under a sheet pile on the downstream side. These are all provided to avoid this thing undermining or piping that we had discussed in the previous sessions. Okay, so here this is a complex problem. So we have to determine the pressure at different points, and also the exit gradient. What is the exit gradient here? The exit gradient should be, the design gradient should be less than the critical gradient. Okay, the critical gradient is what we studied, that is the disturbing force F should be equal to the submerged weight of the soil particle at that particular point here at the exit. So that is the exit gradient. So a complex profile, so if this is a profile, it is divided into a number of simple profiles. So and each profile can be solved mathematically. So first we will consider the upstream pile, sheet pile. Then we will have some, will determine the pressure at different points here. So the it is divided into key points. Say this is C, and then this is D, and then it is E here, like this. C, D, E. Again, here it is, so there, or you can say, you can call this as 1, 2, sorry, this is 2, this is 3, 4, 5, 6, 7, 8, 9. So like it is, so key points. He takes the key points at different simple profiles and determine the pressures by dividing it into simple profiles. So each profile can be solved mathematically. So one profile is taken, and then here the pressure here is at 1, 2, and 3 is determined. Then the profile on the downstream side is considered, and then the pressure here 4, 5, and 6 is determined. So like this, it is divided in this complex profile will be divided into simple profiles, and each profile is solved mathematically. So mathematical solutions of flow nets for these simple standard profiles have been presented in the form of equations. So the solutions for this flow nets is given in the form of simple equations. You have to just remember the equations to in order to determine the pressures at various points. So these equations can be used for determining the percentage pressure at various key points. So Laplace has given these equations for the simple profiles like this, and at the key points you can determine the pressures, and finally you can also find the exit gradient. So he has he has divided into three simple profiles. Is divided into three simple profiles. The simple profiles which are most useful are a straight horizontal flow of negligible thickness with a sheet pile line on the upstream end and on the downstream end. So now first we have to divide whatever problem is given. So we will divide it into two simple profiles like this. One profile with the, this is upstream end and this is the downstream end. So there's a sheet pile in the upstream side. So this is the upstream side, and this is the downstream side. Downstream side. So a sheet profile is considered on the upstream side and on the downstream side. So and this key points are noted down. So here it is taken as C1, D1, E1. You remember this? So the key points are denoted as C1, D1. So C at the top, D1 here, E1 here. Then again here it is taken as C, E, and D. The same procedure you have to follow. So you have to name it like this. So here, if this is a pile, so this is your C1, at the bottom it is your D1. Sorry, D1, and here it is E1. E1. So and the downstream side also it is C, E, and D. So how you can determine the pressures at these key points? is by using these formulas. By using these formulas, these are the simple equations he has given to find out the pressures at different points. So what is the pressure at C1? Phi C1 is 100 minus phi E. Phi E is the pressure at this point. Pressure at this point. Near the downstream sheet pile. This is the downstream sheet pile. So you have to determine the pressure at this point. So first thing is you have to determine phi E, and phi C1 can be obtained by subtracting, one second. So once you get phi E is what you'll find out first by using this formula. What is this formula phi E? It is 1 by pi cos inverse of lambda minus 2 divided by lambda. There's an expression for lambda. I'll come to it later on. So for this point, it is minus 2. So when you come down, the pressure will be less than the pressure at E. So because as the water flows from the upstream end to the downstream end, so first it comes to E and then D, and then it again exits at C. Okay. So here the pressure at E will be more than pressure at D, or you can say the pressure at D will be less than pressure at E. So here it is pi minus 1 divided by lambda minus 1 divided by lambda. For E, it is minus 2. For D, it is minus 1. For D, it is minus 1. It is cos inverse of lambda minus 1 divided. You have to remember this set of equations, where lambda is 1 plus root of 1 plus alpha square by 2, where alpha is B by D. B is this length between the two sheet piles. This is the base length, distance between two sheet piles, which will be given in the numerical problem. So this B divided by the depth of the pile. If you are calculating the pressure here, it is this depth of the pile. And you must know that this depth and this depth is same. If both the depths are same, then only you can apply these formulas. If the depth is different, then separately you have to find the pressures for E and D, and then find out what is the corresponding pressure of C1 and D1. That we'll take it up in the numerical problem. Okay, so you have to remember this equation. So phi at E, first you find out phi at E, you have to work backwards. Then you will calculate phi C1, 100 minus phi E. Then phi D you will calculate. Phi D is obtained by phi D1 can be obtained after subtracting from phi D from 100. Phi D is obtained from this formula. For the first formula, it is lambda minus 2. The remaining expressions are same. And for the second formula, it is lambda minus 1. And lambda is a common value for all this. That is 1 plus root of 1 plus alpha square by 2. It is like your solution for the quadratic equation minus b plus r minus square root of b square minus 4ac divided by. It is something like that. So you remember in that way. So it is 1 plus root of 1 plus alpha square divided by 2, where alpha is b by d. B is the length, the distance between the two piles, upstream pile and the downstream pile. And you should also remember that the depth of the pile in both the cases should be same. Okay. And the second case, a straight, when there is a horizontal floor, when an apron is provided, floor depressed below the bed, but without any vertical cutoffs. There are no vertical cutoffs. So normally this problem will not be given. So you don't have to remember this formula. You can just know this. So here the pressure is given by phi d minus of, so phi d dash. First, again here you have to find out on the downstream side, phi d minus of 2 by 3 phi e minus phi d plus 3 by alpha square, and it is phi dash d1. The pressure here can be determined by 100 minus of phi. First you have to determine this, and then you have to determine. Normally this horizontal floor will not be given. You will be given with this sheet piles, and this is an intermediate sheet pile. So a straight horizontal floor of negligible thickness with a sheet pile line at some intermediate point. So this is in the middle. This is in the middle. So as I told you, a complex problem is divided into simple problems. So this is the where, so there will be a sheet pile here, there will be a sheet pile here, or an intermediate pile in between. So here, so first you have to determine at this downstream side, so you will name this as E, then D, and C. Of course, you know what is the pressure at C? It is zero because it is the exit end, it is the downstream end, it is the exit end. Here the pressure is zero. So here this will be C1, D1. What is the pressure at E1? E1 is the pressure which is the head here. E1 is the pressure at, it will be equal to this H, the depth of water, H. So this reduces. So as you come down, so D. So how do you get C1? C1 can be obtained by 100 oh sorry, this is I think this is C. Hmm, yeah, E C1 D1. So phi C1 is equal to 100 minus phi E1. Phi D1 is 100 minus phi D. That is here. Phi C1 is 100 minus phi E. Phi D1 is 100 minus phi D. Yes. And that, so you will get for these two piles the pressures, and then for the intermediate pile we are going to take it separately. So this is the intermediate pile. Again the same name of conventioning the same convention we are following for naming the key points, that is C, E and D. It is taken separately because it is divided into simple problems. The complex problem is divided into simple problems. B1 is the distance of the first sheet pile. B2 is the distance of the second sheet pile. That is the downstream sheet pile. This is the upstream sheet pile, and this is the downstream sheet pile. Okay. So phi E is given by 1 by pi. One intermediate means here C will be there. Pressure at C will be there, pressure at E will be there, pressure at D. So you have to find out phi E, phi D and phi C for intermediate piles. Here E is not necessary and C is not necessary because downstream side it is 0, upstream side E is equal to the pressure here will be equal to H. Okay, so phi is 1 by phi cos inverse of, there it was 1 lambda minus 2. Here it is lambda 1 minus 1 divided by lambda. So here it is only lambda 1. Here it is lambda 1 plus 1. That is all the difference. There it was 1 by pi cos inverse of lambda minus 2 divided by lambda. Here you see lambda minus 2 divided by lambda, lambda minus 1 divided by lambda. Whereas here it is lambda 1 minus 1 by lambda, lambda 1 by lambda, because this 1 you remove and again you add 1. This is how you can remember. Uh, okay. Then where lambda is equal to root of 1 plus alpha 1 square plus root of 1 plus alpha 2 square, and lambda 1 is root of 1 plus alpha 1 square minus root of 1 plus lambda 2 square divided by 2. So these formulas you have to remember. Alpha 1 is given by B1 by D. Alpha 2 is B2 by D, where D is the depth of this file. So B1 and B2 are the distance of these files. So you have to remember these formulas. It is 1 plus alpha 1 square plus root of 1 plus alpha 2 square. So instead of plus, here you have minus. That's all. It is alpha 1 is B1 by D, alpha 2 is B2 by D. So when we take up a simple numerical problem, you will understand this better. So in the next session, we will take up a numerical problem. The key points are the junctions of the floor and the pile lines on either side, and the bottom point of the pile line and the bottom corners in case of depressed floor, as I told. So the key points are the junction of the floor. Here, this junction you have to take on either side, this side and the bottom point of the floor. So this is C, this is E and this is D. This is how we designate the key points. So you have to find out at E, D and C for intermediate. For the upstream file, So you have to only find out C and D. It depends upon the value of the pressure on the downstream side. So this will be C1 and sorry, it is C1. Here it is E1 and D1. D1. So C is 100 minus 5 at E1. D is 100 minus 5 at D1. Okay. So thank you.